This is lecture 28 of the subject analog circuits. In this class, I am going to discuss about active filters, and firstly we will give the introduction of active filters, types of active filters, and then frequency response of active filters. So, starting with the active filters. So, firstly we need to understand that what is filter and why we need filters. Filters are the circuits which passes a specified band of frequency and rejects the remaining frequencies. Whatever frequency band we want, we can pass it. Whatever we do not want, we can attenuate those signals, we can attenuate those frequencies. This task is performed by filters. So, there are two main types of filters, one is active filter, another one is passive filters. So, passive filters are those filters which utilizes the passive elements. For example, in passive filters we use three components: resistor, capacitor and inductor. If we design any filter with the help of resistor, capacitor and inductors, such filters are called passive filters because R, L, C all are passive elements. Active filters are those filters in which we use active element. Active element, for example, op amp, that is operational amplifier, that is active element. But in active filter, along with op amp we use resistor and capacitor also, but it is called active filter because we are using op amp as an active element in active filters. That is the difference between active filter and passive filter. Now, the question arises that what are the advantages of active filters, why we are more focusing on active filters here. The reason is that since we are using active element op amp here, so we can amplify the input signal, but in passive filters, since there is no active element involved in passive filters, so signals are attenuated in case of passive filters, but there is no attenuation of the signal in active filters because this op amp it provides gain. So, because of this feature of the op amp that amplifies the signal do not get attenuated in case of active filters. So, that is the first advantage of active filters, it provides gain, while the passive filters it do not provide any gain, fine. Another advantage of active filter is there is no loading effect. There is no loading effect, the reason is that when we apply the input signal Vin to the filter, to the active filter. So, in that case we normally apply this Vin at the positive input terminal of the op amp, positive input terminal of the op amp. And we had seen that in earlier classes that when we apply the input signal at the non inverting terminal of the op amp, then the input resistance it is very high, ideally it is infinite, practically it is in mega ohm range. Since the input resistance becomes very high, so of course there will be no loading effect. So, normally in active filters we use the non inverting configuration of op amp, normally we use. The reason is that the input resistance in non inverting configuration it is more. So, we can avoid this loading effect. So, these are the two main advantages of active filters, and of course, the limitation of the active filter is the limitation of this op amp only. If the slew rate of the op amp is limited, if the gain bandwidth product of the op amp is limited, then of course it will suffer the active filters. But since there are many op-amp ICs are available in the market in today's era, which is having good gain bandwidth product, it is having better slew rate than 741 IC. So, we can use this active filter. Earlier what was happening, the slew rate and the bandwidth of the op-amp was very limited. So, it limits the bandwidth and slew rate of the filters also, active filters also, but over the period of time the bandwidth and the slew rate of the op-amp IC, it has been increased, fine. So, the limitation of the active filter is the limitation of the op-amp itself, whatever the limitation of the op-amp will be, that can become the limitation of the active filters. But now here we are focusing on active filters, and since the gain, it provides gain and there is no loading effect, that is why we mainly use this active filter. There are 4 different types of active filters: low pass, high pass, band pass and band reject filter. Band reject filter, that is also called band stop filter, it is also called band elimination filter. Apart from these 4 filters, there is another category, that is all pass filter. That all pass filter passes all the frequencies, but the change in the phase. But here we are going to study only these 4 filters: low pass, high pass, band pass and band reject. So, starting with the low pass filter, since it is low pass filter, so as the name suggests, it passes the low frequency signals and rejects the high frequency signal. What does it mean? It means that when we draw the frequency response of this low pass filter, that is the gain versus frequency, then this low pass filter, it is going to pass the low frequencies, and these frequencies will be from 0 to, let us say that frequency is FH, cutoff frequency, right. So, we can draw the ideal response and the practical response. Here firstly I am going to discuss the ideal response, then practical response, and after that we will be focusing on practical response only. Ideally, if the low pass filter is ideal, that will not happen practically, the response will be like this. Now, see, from frequency 0 to FH is passed, so this is called pass band, and the frequency above FH is blocked. Blocked means attenuated, signal is attenuated. The signals which are having frequency greater than FH, that is attenuated. So, this is called stop band. So, this is the ideal response. In ideal case, in stop band we do not get any signal in ideal case. But practically, when we draw the frequency response, that is again the gain versus frequency, then the response of the low pass filter is like this. This maximum gain, this is called pass band gain, let us say this is AF, right. Now, this FH frequency is the frequency at which the gain is reduced by 3 dB of the maximum frequency. So, this FH is called minus 3 dB frequency. This minus 3 dB frequency, it is also called break frequency, it is also called cutoff frequency, it is also called corner frequency. So, there are different names, but all are same. So, what is this FH? FH is the cutoff frequency, it is defined as the frequency at which the gain is reduced by 3 dB of the maximum gain, right. Now, you can see that again in this case, this is your pass band and this one is stop band, but in a stop band we are getting signals of lesser gain. So, this gain plot, it is reducing, the gain is reducing when the frequency is increasing. So, at which rate the gain will be reduced? It will be decided by the order of the filter. For example, if it is the first order low pass filter, then the rate at which the gain will be reduced, it will be minus 20 dB per decade. If it is second order filter, then it will be minus 40 dB per decade. If it is third order filter, it will be minus 60 dB per decade. So, in short, if the order of the filter is n, then the roll off rate, this is called roll off rate, it will be n cross 22 dB per decade, fine. So, this is called roll off factor, roll off rate. So, this is the frequency response of the low pass filter, and the important terms are like pass band gain and cutoff frequency. Now, another filter is high pass filter. So, as the name suggests, in high pass filter, high frequency signals are passed and the low frequency signals are rejected. So, when we draw the frequency response of this high pass filter, when we draw the ideal response, then the gain versus frequency curve, it will be like this, right. Let us say the cutoff frequency in high pass filter is FL, fine. So, we can see that in high pass filter this one is stop band, because in this band from frequency 0 to FL no frequency is passed, but the frequency above FL we are getting gain, means the signal is getting passed. So, this is your pass band, but this is the ideal response. Practically, when we draw the frequency response of the high pass filter, that is the frequency versus gain, and this gain is basically the voltage gain, that voltage gain is in dB, that voltage gain is in dB. Voltage gain is, that is output voltage upon input voltage, V naught upon Vin, V naught upon Vin, that is ratio. So, when we convert it into dB, it will be 20 log mod V naught upon Vin. So, on y axis the gain is in dB. So, practically the frequency response of high pass filter is this one. So, in this case this is pass band and this one is stop band. Again the maximum gain of this response of this filter, that is called the pass band gain AF. AF is the gain which we are getting in the pass band, and again the cutoff frequency is, it is the frequency at which the gain is reduced by 3 dB of the maximum gain. So, in high pass filter let us denote it with FL, let us denote the cutoff frequency with FL. In low pass we had denoted it with FH, in high pass we are denoting it with FL. You can take any symbol, there is no issue in that. So, this is the frequency response of high pass filter. Again the roll off rate, here you can see that the gain is increasing. For first order high pass filter the rate will be 20 dB per decade, for second order it will be 40 dB per decade, for third order it will be 60 dB per decade, right. Next filter is band pass filter. So, band pass filter is the filter which passes a particular band of frequency and rejects the remaining frequencies. What does it mean? It means that when we draw the gain versus frequency response for band pass filter, so the ideal response will be like this. So, here we can see that let us see, let us say this is the cutoff frequency FL, this one is FH. So, this band pass filter, it will be passing the frequency from FL to FH. So, this is the pass band, and the frequency from 0 to FL, it is getting attenuated. So, it is stop band, this is stop band, but this is the ideal response of band pass filter. Practically, when we design the circuit and plot the frequency response of the band pass filter, practically the response of the filter, it is like this. So, in this case again this is the pass band, this is stop band, this is stop band. Now, in case of band pass filter, there are two cutoff frequencies. One is called FL and the another one is called FH. So, FL and FH are the cutoff frequencies of the band pass filter. This FL is called lower cutoff frequency and FH is called upper cutoff frequency, and the maximum gain of this band pass filter, let us say this is AF, or we can say it is AM also, we can denote it AF or AM. AM is the mid band gain. Mid band gain means since we are getting the maximum gain in the mid band, that mid band is from FL to FH. That is why whatever gain we are getting in this frequency band FL to FH, that is called mid band gain. And again the definition of FL and FH are same. FL is the lower minus 3 dB frequency, FH is the upper minus 3 dB frequencies. So, what will be the roll off rate? The roll off rate here, it will be 20 dB per decade, and here it will be minus 20 dB per decade, right. So, we can see that the minimum order of this band pass filter, it will be 2. The reason is that since when we get a 0, then the rate will be plus 20 dB per decade, then again we will get a pole, then plus 20 minus 20 it will become 0, then again we will get a pole, then it will become minus 20 dB. So, at least 2 poles are required to design this band pass filter. 2 poles means 2 order is second order. So, we can not design the first order band pass filter, the minimum order is 2, but in case of low pass and high pass we can design the first order low pass, first order high pass, right. So, this is about band pass filter. Now, the types of band pass filter. There are 2 types of band pass filter. First one is the wide band pass filter and the second one is the narrow band pass filter. So, the wide band pass filter, narrow band pass filter. Wide band pass filter, as the name suggests that it passes the wide band of frequencies. Narrow band pass means it passes the narrow band of frequencies. So, how we say that whether it is wide band pass filter or narrow band pass filter, it is decided on the basis of the quality factor. For wide band pass filter, the quality factor Q is less than 10, and for narrow band pass filter the quality factor Q is greater than 10. Now, what is this quality factor Q? This quality factor Q, it is defined as center frequency Fc upon bandwidth. Fc is the center frequency. So, of course, you can see that if bandwidth is more, then the quality factor will be less. That is why you can see that for wide band pass filter bandwidth is more, quality factor is less, and for narrow band pass filter vice versa, right. This center frequency Fc for this band pass filter, it is under root Fh into Fl. Fh is the upper minus 3 dB frequency, upper cutoff frequency, that is also called, and Fl is the lower minus 3 dB frequency or lower cutoff frequency, and the bandwidth of this band pass filter is Fh minus Fl, right. So, these are some important terms, equations for band pass filter. Now, next one is band reject filter. Band reject filter, it rejects a particular band of frequencies and passes the remaining frequencies, just opposite of the band pass filter. What does it mean? It means that when we draw this frequency, when we draw the frequency response of the band reject filter, that frequency response, it is the graph between gain versus frequency. In ideal case, the response will be like this one. So, you can see that from frequency FL to FH, we are not getting any gain. In fact, in band reject filter, we just reverse this FL and FH. So, we say that this is not FL, this is FH, and this is not FH, this is FL, right. So, in band reject filter, the frequencies from FH to FL are rejected. Now, the reason why I have taken this FH first and FL later, just not to get confused, this FH, it is the cutoff frequency of the low pass filter, we have already mentioned that, right, and FL is the cutoff frequency of the high pass filter, and we can see that this portion, it represents the frequency response of the low pass, and this portion, it represents the frequency response of the high pass. That is why here in this case we have mentioned FH this one and FL this one, but in the previous case the graph was like this, right. So, there we had mentioned this is FL, this is FH, but this is for band pass filter, but in case of band reject just FL and FH are reversed, right. Just do not get confused with it, I want a single terminology to be used throughout the class, right, that is why I am using it. Now, see this band reject filter, it is also called band stop filter or band elimination filter. So, this is about the ideal response of the band reject filter. When we draw the practical response of this band reject filter, that is the gain versus frequency, the response is this one, fine. So, this is your cutoff frequency, that is FH, and this is another cutoff frequency, that is FL. This is stop band, this one is pass band, this one is pass band. So, in band reject filter a particular band of frequency is getting rejected and the remaining frequencies are passed, that is why it is called band reject filter, and this is the maximum gain, let us say this maximum gain is AF. Now, there are two types of band reject filter. The first one is wide band reject filter, which rejects the wide band of frequencies. The second one is the narrow band reject filter, which rejects the narrow band of frequency. This narrow band reject filter, it is also called nose filter. This nose filter is very popular term. Normally we use this nose filter term it is used more than narrow band reject filter. So, nose filter is very important. So, again we have classified these two band reject filters, wide and narrow, on the basis of the quality factor. Again, for wide band reject filter the quality factor Q is less than 10, for narrow band reject filter Q is greater than 10. So, this is about band reject filter, and I have discussed the frequency response of all the 4 active filters: low pass, high pass, band pass, band stop filter, right. So, the point is, in passive filter, like if I take the example of passive low pass filter. So, in passive low pass filter we are using only two components R and C. This is the first order filter, this is input V in and this is V naught. This is your passive low pass filter, and when we use any active element along with this R and C, then it becomes active filter, right. So, when we combine this structure RC structure with operational amplifier, then it becomes active low pass filter, right. So, we will see in further classes about low pass, high pass, band stop filters. We will study the circuits of these 4 filters. There we will go into detail of these 4 filters. So, in this class I have basically given the basic introduction of 4 active filters. This is the reference.